Okay, this is the lesson video for section 3.1 on implicit differentiation for AP Calculus BC. And what we're going to talk about here today is the idea of taking the derivative typically when we have equations where we can't isolate the y and get the y in terms of x. So the big thing to remember here is all we're really doing is the chain rule. And that's what I'm going to talk about at the beginning here. We've actually been doing the chain rule on every derivative rule that we've talked about. We just haven't really needed to use it until we get to situations like this. So with implicit differentiation, what you're doing is you're taking the derivative of the equation in the form that you get it in. So I'm going to show you a few examples here at the beginning to get you a feel for how this is going to work, and then we'll jump into some equations. So for example here, I've got the derivative with respect to x of x cubed. Well, everybody knows that that would be 3x squared. But the other part of that is, if we did the chain rule, that would be multiplied by dx dx. Well, dx dx is just 1, so typically when it's an x expression, we don't write that out because it's not necessary. However, when we look at this next one, ddx of y cubed, well, if I take the derivative here from the outside in, my power rule gives me 3y squared, and then the derivative of the inside is dy dx. So what I have is 3y squared times dy dx, and that's my derivative. Now for the next one, you kind of get the idea once you see that one. I've got the sum of two terms here. The derivative of x would be 1 times dx dx, so it's just 1. And then that would be plus 3 times the derivative of y with respect to x, whatever that is. Okay, so that's not a 1, so we have to write it. On this last one, I'm going to use the product rule. So the derivative of x would be 1, so 1 times y squared, plus x times the derivative of y squared, which would be 2y times dy dx. So I'm going to get 2xy dy dx. Okay, so where we will use this a lot are on situations where we've got, like I said before, equations where we can't necessarily isolate y. All right, so let's look at the two methods that we've used. So the first method is what we've been doing up to this point, which is called explicit differentiation. That's when we have y in terms of x. Second method is called implicit differentiation. And that's the method where we just take the derivative of the equation in the form that it's given in. Okay, so let's take a look at an example of these two methods side by side. So what I have here is an equation, y cubed is equal to x to the 7th power. The easier way to do this one would just be to isolate y. And you can see we get here y is equal to x to the 7/3 power, do the power rule, and we've got our derivative. And the nice thing about the derivative is we just have the derivative in terms of x. The other method, though, which really we wouldn't use here, but I want you to see it, is just take the derivative of the equation in the form that it's in. So I'm going to take the derivative on the left side. That's where this 3y squared dy dx comes from. And then the derivative on the right side is essentially just 7x to the 6th. So I'm trying to solve for dy dx. All I've got to do is isolate dy dx using some simple algebra, and you can see we get this derivative. Now that derivative is actually equivalent to the one that we just found. But you can see it's got a disadvantage to it in that in order to evaluate this derivative, I have to know the x and the y coordinate to know the derivative at that point. Okay, so I said these are equivalent even though they look different. And let's talk about why that's the case. So I've got two equations here that look a little different, but I'm going to take that second one, which was dy dx is equal to 7x to the 6th over 3y squared. Now take a look at what we have up here. When we solved for y, we said y is equal to x to the 7/3 power. Well, I'm going to substitute that in here. So 7x to the 6th over 3 times x to the 7/3 power squared. And now I'm just going to do a little bit of algebra to simplify this down. Well, I have x to the 6th over x to the 14/3. That's going to give me x to the 4/3, so we end up with 7/3 x to the 4/3 power. So we get the same result once we eliminate that y from the derivative expression. So you can see both methods give me the same answer. And like I said, the reality is I wouldn't use implicit differentiation here because I can get a nice simple derivative in terms of x with very little effort. But you can see both methods are indeed valid. They give me the same result. Okay, so primarily what we're going to do here for the rest of the time is just work through a couple examples. I'm going to show you one, and then I'm going to have you try a bunch of these and just check through your work as I explain some of the basic steps. Now, primarily what you're going to find is the derivative will be the first step, and then after that, you're just going to have to do some algebra. And the more of these you do, the more steps you'll be able to skip. Okay, so here's the main idea when we're trying to do implicit differentiation. Typically, we're going to be looking for dy dx. We're going to differentiate both sides of our equation without worrying about trying to isolate y. Then, once we've taken the derivative, we're going to go ahead and isolate dy dx. Okay, so here's a couple of examples. I'm going to work through the first one. We've got x squared plus y squared is equal to 25. And I put a diagram over here just so we can look at the results and kind of verify what we're seeing in terms of a derivative. So I'm going to take the derivative in the form that it's in. That would give me 2x plus 2y dy dx. And I also have to take the derivative of the right side of the equation. And this is the step that people tend to forget on this. The derivative of 25, when I take the derivative with respect to x, is just going to be 0. So in the end, when I isolate my dy dx, I'm going to end up with dy dx is equal to negative x over y. So that's my derivative. Now, again, notice my derivative has an x and a y in it, which is not the best. However, in this case, if I had tried to isolate y, I would have had a plus or minus square root, which means that I've got two branches to my equation when I try to write it in function form, and that means my derivative would also have two branches. So in some ways, it's a little bit advantageous here to actually write this in terms of x and y, so I only have one derivative equation to deal with. Now, if you just look over here, you can kind of verify quickly the solutions that we just found. So, for example, if I am at a point where x is equal to 0, like 0, -5, or 0, 5, I would expect at those points that I'm going to have a 0 slope, and you can see that you do. Or if I'm at the point 5, 0, or -5, 0, I would expect an undefined slope, and you can see you do get an undefined slope. And the last part, if I just look in my quadrants, I can kind of think about, does this answer make sense? Well, if I am in, let's say, the first quadrant, that means that x is positive and y is positive. Let's say I'm at a point out here. That would be a negative slope, and you can see I do get a negative slope. You can kind of approximate and see how those would match up. Okay, so when we graph these things, we can verify our answers. Sometimes graphing these is a little more difficult, so we usually don't verify answers graphically, but I just wanted you to see that so you can actually see that what we're doing matches up with the graphical behavior that you have. Okay, so here's another example that I want you to try. This one's a little more complicated. You can't isolate y, so don't even try to mess around with it. Just try to take the derivative here implicitly and see if you can get dy dx isolated. So pause the video, take a minute, work through that, and when you come back, I'll show you the solution. Okay, so here's what you should have ended up with for that one. You can see that on the first step, I didn't try to do any algebraic manipulation. I just took the derivative of the equation in the form that it was in, and I got 3x squared plus 3y squared dy dx plus 9x dy dx plus 9y. So that second piece of it, this is all the result of doing my product rule. Okay, and then on the right side, the derivative of 0 is 0. That's all the calculus that I'm going to do in this problem. At that point, now it just becomes an algebra problem. How do I isolate dy dx? And you can see that I grouped the dy dx terms together and factored out dy dx. I moved all the other terms to the right side of the equation, and then I just divided by 3y squared plus 9x and simplified down. So your answer could look a couple of different ways. Notice this answer is not really wrong. It's just not completely simplified. So typically we would either have that written as an answer or that one. Either one of those would be fine. They're both equivalent. It's just a matter of, if you're going to check your work, whatever the answer key says, try to match that form. But other than that, either one is totally fine. Notice though, with the derivative, I do need to know the x and I do need to know y at that point in order for me to be able to evaluate the derivative. Okay, so let's take a look at a couple more examples. So over here, I've got two more that I just want you to try. So I want you to work both of these. So pause the video, work through both of them, try to isolate dy dx, and then when you're done, unpause the video and I'll show you the solutions. Okay, and here's what you should have ended up with on those two. So for C, that one's pretty straightforward. We're starting with the product rule. The derivative of y squared is 2y dy dx. The derivative of 3 is 0. And again, I just want to emphasize this. This is the thing that people tend to forget. Don't forget to take the derivative of the other side of the equation, and if it's a constant, the derivative is going to be 0. And then it's just isolating dy dx. Now notice on this problem, I didn't show any intermediate steps. That's really where I want you to get with implicit differentiation. I want you to get to the point where you show your first step where you do your calculus, and then you jump straight to your simplified solution when possible. So this one, you know, everything kind of works out the same way. After a while, you'll start to see a pattern in how things are going to work. And when you start to see that pattern, you can start skipping a lot of steps. So in this case, negative y over x plus y. For the second one, it's a little more complicated because we've got a sine xy. So you've got to be careful with your chain rule here. And when you do your chain rule, notice on this piece of it, this is the derivative of the sine. This is the derivative of x times y. And then on the right side, the derivative of 2x is just 2. Now, that's all of the calculus in this problem. So again, at this point, it's an algebra problem, and then we're just going to isolate dy dx. So my answer that I wrote looks like this. It's also perfectly possible that if you were looking at an answer key that would have gotten a common denominator, we could do that if we wanted to. We could get a common denominator, but that's a perfectly acceptable answer. All right, let's take a look at a couple more here. So for the next one, what I want you to do is I want you to find dy dx, and I want you to find the equation of the tangent line, and then I also want you to find the equation of the normal line. Okay, so nothing really different than what we did before. It's just that now we're using implicit differentiation. So pause the video, work through this problem, and when you come back, I'll show you the solution. Okay, and here's what you should have ended up with. You can see that the derivative here looks kind of messy, but it's not really that hard to work with. I wanted to show you, I did this one a little bit differently on purpose. I know I never actually isolated dy dx, and I did that on purpose because let's say the problem didn't say find dy dx. Let's say this part was not there. If all it said to do was take the equation of the tangent line, then what would make this easier for us, rather than going through the extra steps and doing all the algebra first, I can actually just substitute my point in first and then just solve for dy dx. So I went ahead and substituted in the point 1, 2, and now rather than having to mess with all of those variables, now I've just got constant values, and this becomes very, very simple to solve for dy dx. And you can see I got negative 49 over 40 as a slope, and then I've got my equation of my tangent line over here. Now, technically, in this problem, I should have found dy dx, but I just wanted to show you that if it doesn't say find dy dx, you actually don't have to go through and isolate dy dx first, and a lot of times you can actually save yourself some work. All right, so for the second part of this, we've got the equation of the normal line, and that's really simple. We've done enough of those at this point. To get the equation of the normal line, it's the same point. All we have to do is take the negative reciprocal of the slope. All right, and then I've just got one more thing here that I wanted to show you. It's kind of a special case, but this shows up from time to time, and the idea of orthogonal, I've mentioned before, is something that's going to show up a lot in physics. If you take multivariable calculus, you'll start to see orthogonal vectors a lot. This is the idea of orthogonal curves. When we talk about two curves being called orthogonal, what we are referring to there is that at any point of intersection, the tangent lines are perpendicular. So it has to be every point where the curves intersect. So if there's one point, we have to check that the derivatives are going to be, or excuse me, that the slopes are going to be perpendicular at those points. Okay, so there's really kind of two steps that we would have to follow here. So the first step is we need to find the intersection points. And then the second step would be to actually test those points. Okay, now in this case, we kind of have one that's a little bit easier because you'll see when we take the derivatives, the intersection points aren't actually going to matter. But if you are asked to ever find whether or not two curves are orthogonal, this is what really we should technically do. We should find the intersection points, and then we should test the slopes at those points and make sure that they're perpendicular. But let's go through. I'm going to call this, I'll just call this equation A and this equation B. So for A, when I take the derivative, xy is equal to 6, I'm just going to take it implicitly. So that's going to give me x dy dx plus, let's see, the derivative of x is 1, so y is equal to 0. And we end up with dy dx being equal to negative y over x. And for the second equation, which I'm calling equation B, when I take the derivative, I'm going to get 2x minus 2y dy dx is equal to 0. And when I solve that, I get dy dx is equal to x over y. And like I said before, I can tell with this one that these curves are definitely orthogonal as long as they intersect, because look at my slopes, they're negative reciprocals of each other. So what I would really need to do at this point is just actually verify that the curves intersect. And I'm not going to show that here because it's just some basic algebra, but you can do some substitution, show that the curves actually intersect, and then you can just say, therefore, since the curves intersect, the slopes are always perpendicular. At that point, then, we have proven that these curves are orthogonal. Okay, so that's not really that big of a thing for us in this course, but I wanted you to see it because it's just one of those special case type of problems that shows up every once in a great while. And it's more of a vocabulary thing than anything else, because if you know the vocabulary, taking the derivatives and testing slopes and doing all of that stuff, that's just algebra. So it's really just a little bit of implicit differentiation followed by algebra to verify what that vocabulary means. Okay, so that's everything in this lesson. The big thing is do enough practice with implicit differentiation that you can start to skip a lot of these steps. This is, a fairly simple process, but it allows us to deal with some equations that are much, much more complicated than the ones we were dealing with before.